All right, hi everyone. This is 𝗍𝗆. I wanted to put together this video because just earlier this week we had a class for CS146S, the Modern Software Developer. It's a class, the first of its kind that we're teaching at Stanford this fall, and the class is all about modern software development practices, basically how we can use AI coding for every single part of the software development lifecycle. Now, in the class this past Monday, we spent the entire class basically going through how we can implement the core of an advanced coding agent like Claude Code or Cursor or Warp in just about 200 lines of code. So we walked through the entire source code, showed that it really doesn't require anything more sophisticated than basic algorithms. And what I want to do in this video is actually go through that same exercise, do a little bit of a screen recording of myself coding up such an agent and show that in about 200 lines of code, we have the core of what powers most of these amazing coding platforms that we've been using. So here we are. That's what this recording is going to be. Again, this is for this was done this past week for our new class, and if you're curious and following along, the course materials are at this URL, themodernsoftware.dev. We post all of the lectures, lecture slides, assignments, and readings, so anyone is more than welcome to follow along. But for the purpose of this thing, let's actually dive into some code and see how very quickly we can build the core of a tool like Claude Code, which is just awesome. So what I have here is the starter code for what we're going to be building. I already put together some scaffolding. It's about 60 or 70 or so lines. The way to think about this is there's nothing super crazy going on here. We're initializing an API client to some underlying model provider. It could be OpenAI, it could be Claude, it could be literally anything, but here we're just using OpenAI for our purposes. We're going to fill in a system prompt later, so this is just left blank. There's some formatting strings just to make it easier to color the outputs of our what we print to the console, and so you'll see the differences in the colors. There's a really simple utility that we put together, which is just a way to go from the name of a file to the absolute path of the file. So we're going to use this later, and it's just going to be helpful for the agent to actually open up files when we implement those things. The core of what powers this agent is really going to rely on three tools, right? So three tools that we're going to use to do so. The three tools that we're going to have to implement are read file, list files, and edit file, okay? So the way to think about any coding agent today and what it really does is it's actually quite simple. So it's a chat, right? Me interacting with an LLM, and when I issue a request to the LLM, maybe asking it to create a new file or something like that, it will return something to me, which its response may include lists of tools that I should be using or issuing. So I might tell the LLM, hey, make me a new file, and the LLM might issue a tool such as edit file with the arguments of what I should be editing. Now I, as the recipient of the tool, will receive that, in this case JSON we're going to implement, but you could format it however you want. And then I'm actually going to execute that tool call, right? So I myself, the user, am executing this tool call. Or I guess in a lot of cases the IDE or Claude Code is executing the tool call, and then we return the response of that tool call to the LM. And so the LM, then we just kind of append this to a running context, like a conversational context with what happened when we issued the tool. And the LM receives that, uses that context to then follow up. We might also issue another query with that context, like some other user prompt, and then the loop just continues indefinitely. So that's really the core of the loop, right? I issue prompt or message to LM responds and detects whether or not it needs a tool to kind of service the request, and then based on that, either we're gonna issue the tool call, execute it, offline, so not by the LM, and we'll return the response of the output, or we're just gonna keep having a normal conversation, because not every time that we say something to the LM are we going to have to actually interact with tools. But anyway, so the crux of this is there are some tools we're going to have to implement, and make available to the LLM, to the agent, to actually use. And so these are the three tools that we're really going to need. That's the core of what's going to power this agent. And we're going to have this kind of like tool registry or tool, it's just like a mapping from the tool to its implementation. And then there are these two other utilities, get tool, stir representation. As we'll see later, this is just going to be a way to actually take any given tool's implementation, return a stringified representation, which we're going to use to then feed into a full system prompt. Because remember, we didn't actually, we didn't implement the system prompt yet, or we didn't write it, but eventually we will, and we're going to need to have a sort of a collection of all the tools that we have available to do that. And then we're going to have an extract tool invocations, which is going to be responsible for receiving the output of the LLM that might tell us to actually, issue a tool, execute a tool. And so we have to parse that from the LLM's output. We're going to have a function to execute LLM calls, and this is just going to be a really simple function to interact with the clients that we've defined above. And then we have the core of the agent loop, the coding agent loop. And this is really going to be the workforce of kind of running through that sequence that I've described. So that's the core of it. By the end of this video, we'll have implemented about maybe 100 to maybe 150 lines of code, powering all of these and implementing all of these. So that sounds good. Let's get into it, and I'll be talking through this as I code, and then hopefully that's something you guys can refer to. Okay. To start this, we're actually going to implement the loop first, right? The core loop of the agent. And for our purposes, I'm going to really just start by printing out our full system prompt. This is just going to be useful for debugging, and then we're going to use it as we build out the rest of the components to iteratively kind of see that we're changing that prompt. So we start by initializing this conversations object, which will really just keep track of all the messages that we sent to the LLM, and anyone that has maybe issued API calls to GPT or Claude or something like that is maybe familiar with this format, or 𝗯𝗯𝐴. This is just the kind of standard message format that a lot of these LLMs currently use. So what's the role of the message, of this particular message, and what's the content of the message? So we're starting with the system prompt, so we're going to issue the system prompt. And then the core of the loop starts by saying, well, while true, so loop this indefinitely, start by getting the user input. Okay, so we're going to get the user input. We're going to use something pretty simple here. You can see now this is where we made use of those like 𝗠𝗎 code escape strings that I had at the beginning. This is just going to color the U, in this case, a different color. And we're just going to do that. Nothing crazy there. Just a little space. And then if this doesn't work, we're just going to be defensive in our programming, and we're going to catch keyboard interrupts and add file errors. And that's just so we can Control-C and Control-D if we want to break for whatever reason. As we're debugging, we're going to break out of the loop. Okay, cool. So we have the user input. We're going to start by just appending that user input to the conversational history. So here, in this case, the role is user rather than system, and content is just user input that we strip out just to clean up any trailing white space characters. So now we receive the user input. And now we have to go into the loop of what the agent is doing, or what the LLM is doing. So this is going to be one more nested while true loop. So let's actually issue, get a response from the LLM. So we're going to execute the LLM call with the conversation history that we've been built out, which in our first run of the loop will only have two messages, the system prompt and then the user message. And then we're going to, once we issue the response from the LLM, which may or may not have tools mentioned in the response as we described, we're going to extract the invocations of the tools. So let's start by extracting the tool invocations from the system response, as we want to do. And we have two different cases. If there are no invocations, if there's no kind of tools explicitly mentioned in the string, we're going to just continue as we normally would. But let's first print the assistance response from this. Again, we're using a different 𝗠𝗶𝗃 escaped string just because we're using a different color. Okay. And we're going to just provide the assistant response here, which is what we want. And then we're going to append that to the actual history of the conversation that we're running. In this case, though, of course, the role is system, and the content is the actual assistant response, as you expect. However, and then we want to break this. We want to just break out of this, so we don't, because if we're just continuing, if the LM is responding and we have no tools to call, then we should just go back to the user and kind of go back to the very top of the loop. And then if that's not the case, let's again print the LLM's response. A bit redundant here, but you know, I'm not saying this is the most clean and perfect code, but it's relatively condensed. So there's a bit of redundancy here, but let's just do that. Again, we're going to append this. So why don't we just copy this? Okay. We're in the second case here, though, where we have to iterate over tools, because the second case, the first case was we have no tools invoked. The first case is with no tools invoked. The second case is we actually have tools that the LM has said we should interact with. So let's do that. So in order to do that, this object will presumably be not none, and we're going to iterate over the object. Now we'll show later what format the function is expected to return when we call extract tool invocations, but to give you kind of a look ahead or give you a little bit of taste of what's to come, it'll be like a list of objects, tuples, names, where one is the first entry of the tuple is the name of the tool to call, and the second was the arguments of the tool that we should call. So that's what that's going to look like. We're going to print this just for debugging, and so we see what's going on. And we will start by first getting the tool. So we'll use the name of the tool that we extract from the tool invocation to get the tool. And then we have a few different cases, okay? If the name of the tool is read file, which we had listed up here, this is the actual key to value mapping. So if it's read file, we should in theory call read file tool, but for our purposes we're just gonna print read file called, because the existing read file implementation doesn't really do anything. But if it's list files, then we'll just list files called, and then if it's edit file, we'll print edit files. Again, we're going to fill this in later, but we're just going to leave stubs here for now. And then, of course, we could have like an else catch-all. If an existing other tool is called, we should, either throw an error or tell the user to, try again. We're not going to do that for now, just in the interest of time. Okay, and then at the end, we will append, again, the output of this tool call. This time it is, because we are issuing the tool, not the LLM, we are receiving the tool name, issuing it, and then returning the response. The role in this case is the user, so it's actually a user message. And the content here will be a particular format that we define, but let's just, the format is as follows. When we return the output of the LLM, of the tool call, we'll prefix it with tool result, and then we'll say, just dump the actual response of that. JSON.dumps response. We need to make this an F string so it can do that. I should probably initialize resp to something here. Maybe like resp, we'll just call it blank for now. Actually, this is probably error, so maybe we should just do this. We're going to fill in response when we actually get the response to the tool calls. Okay, we're almost at something that's useful. Okay, in order to make this useful, because right now if we ran this loop, it really wouldn't do anything. To make this at least mildly useful, we're going to start by issuing or implementing the execute LLM call. So the way we do that is we're going to start by, again, it's like a pretty simple function, because all we're doing is interacting with the OpenAI client, which does the most bulk of like the actual talking to the LLM. And so the way we're going to do that is we're literally just going to say response equals OpenAI client dot chat dot completions dot create model equals GPT-5, message equals messages equals conversation, as we would expect, and then max completion tokens equals, let's just say 2,000 to be really aggressive. This is probably way more than we need, but just to be on the safe side. And then what we return at the end is response.choices0.message.content. Okay, so at this point we have implemented this function to interact with the actual OpenAI client, and that's just going to issue a call to the LLM and then return a response. Now, one thing that we have to include is actually we're going to just initialize, rather than a stub that says pass in the get full system prompt, we're actually just going to return an empty string, just because we're appending this to the conversation, and that's what we're providing to the LLM, so we shouldn't provide none messages to the LLM. But at this point, we actually have something that we can at least talk to, and not do anything useful because we haven't hooked in the integration of the tool calls. So look at this. Hello there. Yeah, so again, all this is doing, the loop without the tool calls is literally just a conversation loop where we issue something to the LLM and the LLM returns with a message, and then we just keep going like that indefinitely. So there's nothing super crazy here. It's not yet a coding agent, it's just a chatbot, really. Okay, to get it to a point where it's more interesting, we have to start implementing the core crux of the other aspects. So there's a few pieces that we're going to implement, and then we're going to run this again. The first piece that we're going to implement is a kind of fleshed out system prompt here, right? So that's what we're going to implement, is actually just put in some of the meat of this system prompt into, which will describe the behavior of the agent. And then we're going to fill in some of the implementations of the other functions. So let's start with the pulling in the meat of the system prompt. So we'll start by saying you are a helpful coding assistant whose goal is to help complete coding tasks. Okay, this is defining the role. You have access to a series of tools you can execute. Even though it's not actually the one executing, we're the ones executing, but just tell it knows what it can execute. Here are the tools you have access to. And in the string, this is going to be our tool list stir. This is going to be something we fill in with another function later that you might remember we stubbed out. Okay, now, really important part, we've described what's the format of the output that the LLM should return if it wants to use a tool. When you want to use a tool, reply with exactly one line in the format tool. So a string prefix, and then specifically the tool name, JSON args, and nothing else. Okay, so literally just a single line when you want to return a tool call. Use compact single line JSON with double quotes. After receiving a tool result message, you should continue with the task. If no tool is needed, respond normally, right? So if you wanted to issue a tool LLM, output this format with the tool name and the arguments, make sure that it's single line compact JSON, and then after we execute the tool and return the tool response using this tool result format, which you'll remember from down here, like this, then proceed forward. Okay, so that's the core of the system prompt. That's all we need to describe to it. Okay, let's now start by putting in these two bits. First is the kind of tool representation that we want to provide to the LM. So to get the full tool representation string, we're going to first start by getting, in this function we're being provided the name of a tool. Let's actually get the tool, just the single tool representation for this tool. So we're going to do that. It's going to look something like this. It's arbitrary how we define this, but for our purposes, we just have to be explicit about what the name of the tool is, what it's doing, and sort of like a signature definition. That's the kind of explicitness that the LM needs to know in order to reason about that tool. So we have the name, we got the description, and that'll be just from the doc string. This is going to make it that we have to be very explicit about our doc strings when we define our tools, as we'll see later. And then we have a signature. Signature. So there's just like a Python built-in that allows us to actually get the signature from the defined tool. So it's important that we have all these like type definitions both within the inputs and the outputs. Okay, now we get so that's getting one tool's string representation. But when we want to inject that into the system prompt and into that dynamic variable that we have defined, we're going to want to fill in the entire thing. So let's do that. We're gonna, there's a tool lister. We're gonna in tool registry, tool list, tool stir repr equals plus equals. We're just gonna append to it. And our format is a bit arbitrary, but we're gonna define it something like this. Of the tool name. Okay, so tool, there'll be a new line, these like triple equal signs, add a single tool lister representation, and then we're gonna demarcate the end of that tool call, and then if we have to go over multiple tools, tool definitions, then we're just gonna make sure there's a line separating them. Pretty arbitrary. Again, you can format this how you want. It just should be, reasonable in terms of something that the LM can parse out and understand the semantics of what a tool is doing and how that separates from the semantics of other tools. And at the end, so we actually have to do this. We're gonna format the tool list stir to be equal to tool stir repr. Tool list repr rather. So this should be tool stir repr. Okay. So this is now going to inject our consolidated definition of all the tools into this thing right here. We have one more thing to implement that's pretty important, significant piece before we can start implementing the actual tool calls. And this is like the function that extracts the tool invocations. So again, what this does is it effectively receives the response from the LLM, which may or may not have one or more tool calls in the response. And we have to parse out those tool calls and then use that to then determine whether or not we need to issue a tool call with the name of the tool as well as the arguments. So the way this function is going to work is it's going to take typically what we'll provide to it, which is going to be like the assistant, the LM's response, and then it'll return a list of tool names and arguments, as we mentioned before. And then, again, because the LM is going to be outputting this format that we explicitly ask across maybe one or multiple lines, we're going to parse that out. So let's do that. Let's see what that looks like in practice. So we're going to keep a list of all the tools that we parse out, because there could be multiple, one or more. And it's going to be quite a bit of a just raw string parsing. So let's start by getting the lines of the LLM's response. So we're going to line.strip, and then if not, line.starts with tool. So this is not, it doesn't have the format that we expect, then continue. Otherwise, we have to, again, this is admittedly somewhat slightly brittle string parsing, but you can make it, of course, more defensive and be more careful about this. But the way we're going to do this is we're literally going to kind of lop off the prefix of the tool call that the LM issues, so take away the tool : prefix, and then we're going to parse out what happens after that, which for our purposes will be it'll be kind of like the tool name and the arguments of the tool. So we need to get the name and we need to get the arguments. So we'll first start by getting the name and the rest of that string. So if the rest of the string doesn't end with the open colon, the open parentheses, then this is like an ill-formatted tool call, and we don't want to deal with that because who knows what it is. So we're just going to be slightly defensive here and say if it doesn't end with this thingy, this close parentheses, then continue. Don't go forward. Otherwise, it should be well formatted, right? It should be something like this. So we're going to take everything up to the end of that close parentheses, and we're going to just load it because we're expecting it to be JSON, because that's how we explicitly ask the LM to produce JSON, compact single line JSON. And then we're going to append both the name and the arguments to this running list of invocations. And then if there's some exception that happens, move forward. Again, we could be more explicit about the exceptions. This is obviously not the best way to write this, but just for our purposes, we want to kind of see what happens. Move forward, and then we're going to return the invocations. Okay. We're at a point where we have the core crux of the loop. Now, we're still not able to do anything useful or interesting yet because we don't have any other tool implemented. So if I just ran this again, it would look very similar to what we had at the beginning, which was just talking to a chatbot. So let's implement one tool, the first tool, and then hook that up to then see what happens when we have this loop. So the first thing we're going to implement is the simplest one, right? It's the read file tool, which, as the name suggests, allows us to read files. So there's a few things to note here. One is because when we get the tool representation for the LLM, we extract the doc string, we extract the signature. We have to be very explicit about some of these aspects. So in particular, the doc string should be pretty descriptive. This is something in general you need to know, is when defining tools for LLMs to use, be explicit, be particular about what they're doing. Don't just expect that, oh, if I define the function, then the LLM knows what to do. No, it's using the doc string to actually reason about what the tool is doing and whether or not it should use it, at what point in time it should use it. So we're going to describe in fairly explicit detail for something that seems very simple what it does. So get the full content of a file provided by the user, okay? And we define the parameters, which in this case is just file name, the name of the file to read. Again, annoyingly, maybe obvious, but again, we have to be explicit. The return should also be clear, full content of the file. It's pretty important to follow to make it easy to parse this, right? So adding these colons ends up being really helpful for parsing. Now the actual implementation. So first, let's get the full path. So this is why we had this utility for resolving the absolute path. We're going to provide that in there. And just for debugging, we're going to print the full path. And then we're going to get the actual content. So let's see that. As f content was f.read return of file path content is just the content. All right, let's wire it up. We have this implementation. So remember how we had stubs out here in the actual loop? Let's actually make tool calls, right? Which is what we have to do as the people that are interacting with the LLM. So we got the name of we have the tool from our registry here. We're going to get file name. And that's it. This should be enough to actually interact with the first tool. So let's see what happens. Okay, so as you'll see here, now we have the system prompt that we printed at the beginning for debugging, right? This thing up here, sorry, way up here. This is what it looks like, right? So we have like the kind of first part of this. Oops. Maybe I need to let me just. Oops. I think I started a debugging session. Sorry about that. Maybe just run it again. So your helpful coding assistant, as we described in the system prompt, here are the tools you have access to, and then here are the representations of the tools. Most of them, like the edit file and list files, doesn't really have anything interesting. So all it has is the name and the signature, which extracts from the input and the types of the output that I use type definitions for. But the tool, the read file tool, actually has something more interesting. It has the description, which is taking the doc string, right? And this is what allows the LM to reason and to know when to use the read file tool. Now, let's give that a shot, right? So we have something here. We have like a few files in this directory. So this file in particular will print and say, okay, what's in test file.py? Okay, you see the assistant issued a read file, a command with our compact single line JSON, as we would expect. Awesome. It detected the file name from my request, resolved the file name to this path, and then printed out the contents of the file. Is this what's inside the file? Let's see. Yes, it is. It's literally just a very simple 2-line main function printing out this works. Awesome, right? So this is just our first tool that we've actually hooked into the LM that it's able to use to understand the semantics of the tool and then know when it should actually issue the tool based on the user request, which is great. So this is the first step toward the agent. We have 2 more tools to implement before this becomes like really, really awesomely useful. So the next one that we're going to implement, and we're going to go through these implementations a bit more quickly in the interest of time, is the list files tool. So the list files tool is just so we can like point to a directory, say, hey, what's in this directory? And the LM becomes a little bit more autonomous in sort of reasoning through those pieces. So let's start by implementing this. Again, we're going to be very explicit about the doc strings. List the files in a directory provided by the user. The param is the path to the directory to list files from. A list of files in the directory. Full path equals resolve absolute path, as we did last time. We're gonna, create a list of all the files that are there, and the for item in full path.iter dir all files.append file name. So this gives us the name of the file, and then we have a type to the file, which if it is a file, then print file is the string, else dir. And then we're going to return this to the LLM. Again, we need to provide return things because that's what we provide in the tool result. So that's why these are very explicit about being almost like JSON representations, because that's what we will provide and add to the context of the LM. Okay. Let's see what, now this should be able to work. Actually, we need to wire this up to the edit files. Yeah, I think that's basically all we need. So now we should be able to, we have a second tool, our second tool wired into the LM. So what's in the week 2? See, it issued the list files tool. And so it's going to issue that, and boom, this is what is in list file. This is what's in week 2, which is awesome. And we could, go one step further, ask it to, actually open up that file using our read files tool, and then that would be kind of 2-step interaction with the LM. But let's do one more thing to really close the loop and then reach nirvana, which is to actually issue or implement the edit file tool. So let's do that. The edit file tool is probably the most complex of the 3 tools, but it's not crazy. Basically, our edit file tool will either create a new file depending on what's provided as input parameters, or it'll replace existing files, sort of like replace them within an existing string. So first we replace the first occurrence of _, which is the old thing that maybe exists in a file or something, with the new thing we want to replace it to. So either we're going to replace _, with _, in a file. Now if _, is empty, then we're just going to create overwrite file with _. So this is just a convention that we're going to use. If like _, is just the empty string, then we're going to create a new file. Add the path to the file to edit, the string to replace, _, the string to replace with, and return a dictionary with the path to the file, and the action taken. Again, this is just to be explicit in the response so the LM knows what happened. Equals resolve absolute path. If _, is this thingy, namely the empty string, then we're going to write text. We're going to write our string. We'll be explicit about the encoding just to be on the safe side. And in this situation, the response should be created file. So this is if we're creating a file from scratch. Otherwise, we're going to read the old text, UTF-8, and then if we need to first find the _, that we want to replace, so we'll find where that is. But if it's, if we can't find it, which would happen if we call find and it returns -1, then, we need to know that we can't even replace this. We can't replace the _, with the _. So we'll just literally tell the LM, hey, _, not found. We could do something more sophisticated if we discover that the _, is not found. We can reprompt the user to tell us what they want to replace, or do some sort of like make some implicit assumptions. That's typically what IDEs, like these AI IDEs and AI coding platforms do, is depending on tool results, they might bake in their own fallback behavior. But for our purposes, we're just going to keep it really simple. Okay, but if we do find it, then we got to edit. So what we're going to do is we're going to replace old_, new_, the first instance of old_, with new_, and then we're going to write to that. And then we are going to return that. Again, what action did we just take? We just edited the file. Cool. So this is the implemented edit file tool. And then we need to actually wire that into the down in the main coding agent loop. So what we're going to do is we're going to get, we have 3 different arguments we have to provide to this particular tool. One is the path, right? So we're going to get the path. Another is the old_, which we can get, and finally the new_. And that should be it. Okay, so now that we've implemented this, we can actually put it to test. Let's see what happens. So if I run this, I should now be able to say, make me a new file called hello.py and implement hello world in it. Hello.py is the path. Old_, nothing. New_, print hello world. Done. This is exactly what you'd expect. Okay. Edit hello.py and add a function to it for multiplying 2 arbitrary numbers. So first, we get hello.py. We read it. Boom. We saw what it was before. We edit it, right? So the old_, was this print hello world. New_, is the modification with the new function. And then we return the response of this edit. Said, hey, we just added a multiply function. You good? We're good. Look at it. We just produced code on top of code. We edited the existing file. That's crazy. This is the core of the coding agent loop. At this point, we could keep creating new files. We could keep editing existing files. And that's all there is to it. That's all things like Claude Code are doing. That's all, Cursor and whatnot are doing. I mean, of course, there's more complexity, but it's all the filler. It's all the fluff around it, right? Bells and whistles that they add on top of this just to make it more streamlined of a UI. But if you look at what we just did, this is 208 lines of code. And we have a functional coding agent that we could use to write code just by talking to it. Absolutely crazy. I hope you guys enjoyed this video. Again, this was for the lecture that we did at the Stanford course, The Modern Software Developer, where we're talking about all aspects of the software development life cycle and how it's changing because of AI coding. So please follow along. The URL is up here. I'll be sharing this code as well. You can see all of our lecture materials, assignments, readings, etc. At this particular webpage. Please follow along. The Modern Software Dev. Thank you all for watching. I hope you enjoyed that.